The next one, the last one of for today's session. The topic is the contact problem of water droplet erosion by Professor Moskalets.
Dear colleagues, let me present the paper on the mathematical modeling of the water droplet erosion. This phenomenon occurs to the steam turbine blades during the turbine exploitation. The main purpose of this effort is to find the conditions of the erosion. The basic points of the approach are presented at this slide. First of all, we consider the turbine blade as a linear elastic half space and the water drop as a linear elastic sphere. We accepted the well-known hypothesis according to which the water droplet erosion is caused by the plastic strain accumulation. So we use the yield criterion. Firstly, we derive the Hertzian formulae by solving the problem of the contact interaction of linear elastic half space and sphere. Here, Q is a contact force, R is the radius of the contact spot, delta is the approach distance of bodies, E and E0 are the Young moduli of materials. Nu and nu0 are the Poisson coefficients. To find the contact stresses, we use the Popkovich-Neuber solution. According to that, the displacement vector u is represented in terms of harmonic functions b and b0. These functions are found from the boundary conditions for stresses. Using harmonic functions, we find the components of the strain tensor epsilon. After that, we find the stress deviator components. Here we can see how the strains are expressed in terms of harmonic functions b and b0, which I mentioned at the previous slide. After finding the stress deviator, we get the Mises equivalent stress, tau. The Mises equivalent stress achieves its maximum at some depths, as we can see at the picture. Then, using the expression of potential energy of interaction, according to energy conserving law, we can get the droplet velocity. You can see the value of the velocity of a droplet, which impact leads to the plastic deformations. In conclusion, we solved the contact problem of an interaction between the water droplet and the turbine blade as an elastic body and a half space, respectively. We estimated the velocity of droplet causing the plastic deformation. Thank you for listening.
Thank you. Is there any question?
May I ask a question? Do you hear me?
Yes, I'm listening.
Okay. The main question: why have problem for drop for liquid?
Can you please repeat the first few words?
Why you use have problem here? Because you see, the calculation, your calculations has no novelty. The only novelty is why you decide to use this problem, this mathematics, this Hertz problem for your problem. For what droplet?
Do you mean why did I decide
Yes,
to use a mechanic of solid deformable solid bodies for this problem? Yes. Thank you for question. I know that usually for such problems the hydrodynamic approach is used, but we decided to use the mechanic of deformable solid bodies. So why? It's a good question, because this problem was solved by my late scientific advisor, Vladimir Vasilievich Eliseev, and he helped me with the solving of this problem, but unfortunately we had no chance to discuss. Do you know how to say? It's a little bit hard for me to answer this question. I'm sorry.
Thank you very much.